This video is about acid-base chemistry, and specifically I want to talk about the differences between acid-base chemistry in a general chemistry sort of setting and an organic. So we're going to start with a strong acid reacting with strong base. HCl, NaOH. What happens when you mix a strong acid or strong base? Everyone, I hope, should say that you make a salt and water. And so if you're thinking about sodium chloride, you of course recognize that sodium almost always prefers to exist as sodium plus, and the chloride is a Cl-, which means that you really have a Cl- and an H+ floating around, which means that you have a sodium plus and OH- floating around, and so you can then cancel out spectator ions. And so if I asked you for a net ionic equation in a general chemistry context, you might then recognize that this is in fact the reaction that's taking place. So this is all stuff that I expect you already know how to do. The new piece, if you're interested in doing this in organic chemistry sense, is to recognize that we care about the flow of reactions. So this hydroxide minus ion, pair of electrons, is going to come and make a bond to the hydrogen. And when that happens, what we're going to do is kick out the pair of electrons that was between the H and the Cl and push it onto the Cl, making Cl-. In other words, you end up making precisely what we would expect, water, and then sodium chloride will be left over. And to an organic chemist, the question of whether the Cl- and the sodium get involved and make an ionic bond or not is really of no interest. What we care about is the electron flow, and specifically the OH- acting as a base or acting as a nucleophile attacks the H parts of the HCl, which in this case is going to be polarized. It's not going to be H+, but it will have a significant delta plus component to it. And the chloride will have a significant delta-. So this is the electrophile over here. H will be the part that gets attacked. The HCl as a whole is the electrophile. The H is specifically the electrophilic parts of the HCl. So the nucleophile attacks the electrophile. This pair of electrons then goes to complete the reaction. And there you have it. Another way of thinking about this is that the highest occupied molecular orbital in the hydroxide, which is a sp3 lone pair orbital, sp3 orbital with a lone pair in it, is the HOMO, highest occupied molecular orbital. The LUMO, on the other hand, is the sigma star HCl bond. So the sigma star HCl bond, that is the lowest unoccupied molecular orbital. You should be able to draw the orbitals in question in both species and convince yourself that this really is the highest occupied molecular orbital, one of the lone pair sp3, oxygen sp3 orbital. And over here, it is the sigma star that gets attacked. Anyway, for something as simple as a strong acid attacking a strong base, there's really not a whole lot of difference from an organic chemistry mindset, other than we care about the electron flow and we care about the orbitals. So now we're moving on to a weak acid and a strong base. And in general chemistry, this isn't much more interesting than a strong acid and a strong base. The acid and the base will react to form, again, a salt and water, as they always do. And we essentially treat that as a process that goes entirely to products. There is essentially no equilibrium constant. Mix these together, we just assume it goes to completion. All of them react, you make all the water and all the salt that you can. And to some extent, we treat this the same way in organic chemistry. Again, what we're interested in is the flow of electrons. So the hydroxide ion is going to make a bond with the H, which is then going to push its electron density between the OH bond onto the oxygen itself. The product that we are interested in, since we are organic chemists, is actually the acetate ion that's created by this process. And of course, left over is going to be the water, which we don't necessarily care about because it's not organic. And then there's going to be a sodium plus floating around somewhere. And for an organic chemist, that sodium plus is never interesting. So we don't care if it's bound or not. It's a spectator. For all intents and purposes, we don't care. This is the product that we care about. Of course, you can now look at this product and imagine to yourself, well, this has resonance possibilities, so you draw resonance structures, or maybe you start thinking in terms of molecular orbital theory. But there are at least two resonance structures and a resonance hybrid that describe the acetate molecule, and maybe that's all you care about. Once again, the HOMO in this case The highest occupied molecular orbital is going to be an oxygen sp3 orbital, and in this case the lowest unoccupied molecular orbital of the electrophile is going to be the OH sigma star orbital, and that's going to be the LUMO. Once again, this is the electrophile, this is the nucleophile. The thing that does the attacking is the nucleophile, the thing that is attacked is the electrophile. So here's the electrophile, the hydroxide is the nucleophile. So what's the difference between them, Gen Chem and organic? Once again, we care about electron flow, and broadly speaking though, these are describing the same general idea. What we have is a weak acid reaction with a strong base to create new products. In organic chemistry, we care about the identity of these products more, but essentially these go to completion. So far, so good. Nothing is all that different. Moving now to a weak acid reacting with water, and we're starting to narrow in on where things start to deviate. The more interesting differences between general chemistry and organic chemistry. At first glance, we're doing the same sort of thing. You know in general chemistry that if you take a weak acid and you add it to water, what you get is H3O plus and then some counter ion, in this case acetate. But this is no longer a reaction that goes fully to the products. In fact, because it's a weak acid, it doesn't go to the products at all. Equilibrium constant for this reaction is 10 to the minus fifth, which is a small number, which means almost the entire subset of molecules is over on the left-hand side. Only a very small amount of H3O plus is generated. So Ka for this process is 1.8 times 10 to the minus fifth. But in organic chemistry, we first and foremost concerned with the reaction itself, which again is going to be a nucleophilic attack of the water on the acetate, a water on the acetic acid, pushing the electrons onto the acetate, and what we generate now is H3O plus and acetate minus. But the way we choose to represent these equilibrium processes in organic chemistry is pKa, negative log of Ka. And so for this particular process, I would describe it as a pKa of 4.76 as opposed to a Ka of 1.8 times 10 minus 5. pKa is simply negative log of Ka, but the reason why we do it is because we're going to be dealing with very, very, very small Kas. In organic chemistry, we hardly ever have any strong enough acid to push the equilibrium to the right, and so since all the numbers are going to be very, very small, we almost always operate in terms of pKa, negative log K. That turns these into numbers that are easier to remember. So the real difference between organic chemistry and general chemistry, though, is still the presence of the water in all of these systems. This is the difference. Most often when we are doing organic acid-base reactions, there's no water present at all. So what are the acid-base reactions that we're actually interested in? Well, fundamentally, we want to know what happens when we have a weak organic acid reacting with a weak organic base. And the real question is, what is the reaction between these two without water? No water present. So again, when we have a general chemistry problem like acetic acid plus water, the interesting questions in general chemistry essentially amount to what is the pH of the resulting solution, which assumes that you have water present, and what you care about is the concentration of the H3O plus ion. However, in organic chemistry, we are much more interested in, say, what happens when you mix acetic acid together with, say, ammonia in some solvent that's not water. And we don't care what the resulting H3O plus concentration is. There may not be any H3O plus. Instead, our question really comes down to what are the products of the reaction and where does equilibrium lie? So the products can be figured out, same as before, by simply mixing together a nucleophile and an electrophile. The lone pair on the nucleophile will always go to make a bond to the most electrophilic atom in the electrophile, which in this case you're attacking the H, which is the OH sigma star orbital, the lowest unoccupied molecular orbital. The lone pair that's doing the attack is found in a nitrogen sp3, and that's the highest occupied molecular orbital. So this is the sequence that happens, and the result is that you make acetate ion and ammonia. But for the purposes of organic chemistry, what we're interested in doing is not only identifying these products, but trying to decide where equilibrium lies. Is this a reaction that's halfway? Is it far to the right? Is it far to the left? So what I really want to know is, what is the equilibrium constant for this reaction? And I don't care about the actual number. What I care about is a vibe. Is it far to the right? Does it make almost entirely products? Is it pretty far to the left? Is it essentially unreacted? or is it somewhere in the middle? So I want to take a brief step back and cover Ka again from a Gen Chem perspective. What is Ka? What is this number that I've been reporting to you? Well, it is the equilibrium constant for an acid dissociation. Said another way, if you have some weak acid HA and you add that to water, it will form some quantity of A- and some quantity of H3O+. The equilibrium constant for that process we simply call Ka. So any weak organic acid can be described in these terms. Take the weak organic acid, add to it water, and you get A- and H3O+. The number is given by finding the concentration of A- and the concentration of H3O+ and dividing it by the concentration of the weak acid itself. We don't have water in there because it's a pure liquid, so it shows up here, but it's constant, so we ignore it. So anyway, the expression for Ka is always the concentration of the products over the concentration of the reactants, but since water is a pure liquid, we ignore it. That's Ka. However, when we're doing this organic reaction between acetic acid and ammonia, then what we really want to find is K reaction, which will involve products and reactants and can be written in this form. Now I've gone ahead and color-coded the reaction for you, and you might start to recognize something that was otherwise hidden. What I really have is two different Ka reactions. If you think about what the acetate is, it is the conjugate ion of a weak acid. It is the weak base. And this is the weak acid itself. However, I can also imagine NH3 and NH4+ as a similar pair. The NH3 is actually an A- if you will, and the NH4 is actually an HA. The reason why this matters is because people have gone ahead and measured Ka, acid dissociation constants, by putting a whole bunch of weak acids into water, so we have all these numbers. If you want to know whether something will react, what you really need to know is what is the acid dissociation constant for each piece, because we can mathematically equate them to figure out what the actual expression is. So up here at the top, what I've drawn out is a Ka expression for ammonium dissolving in water. Take ammonium, dissolve it in water, and you get ammonia and H3O+. The equilibrium constant for that process is about 10 to the minus 10, which means that the pKa for that process is 10. These numbers are rounded, by the way, but they're the rule of thumb numbers that I remember from the pKa short list. Okay, in order for me to be able to solve the problem I want to solve eventually, what I really need to do is to flip this equation around, and you'll see why in just a second. But for the moment, what I'm doing is putting everything that is on the reactant side to the products and vice versa. And I'm also going to color code the H3O+ and the water so that you can see that these pop out. So the NH3 is now on the left, the NH4 is now on the right. Mathematically, I can do this if I take the reciprocal of the Ka. So rather than having an equilibrium constant that's 10 to the minus 10, I now have an equilibrium constant that's 10 to the 10. Said another way, this top expression is saying that the reactants don't react very much. Equilibrium lies far to the left. So of course, if I flip it around, equilibrium lies entirely on the protonated side. NH4+ is the dominant species. Water is the dominant species. You don't have very much ammonia. Now the reason why I flip this expression is because I now need to add it to the acetate Ka expression that I had up on the board earlier. So acetic acid plus water goes to H3O+ and acetate. The Ka for that expression is 1.8 times 10 to the minus 5. Shorthand pKa for a carboxylic acid is 5. So what I can now do is add these two expressions together. And if I add these two expressions together, I think you'll see that some things cancel. Specifically, water on both sides cancels out. H3O+ on both sides cancels out. And what I'm left with is acetic acid, ammonia, acetate, and ammonia. Precisely what I want. So all I need to know is mathematically what happens to my Ka. Well, what happens is K reaction is just going to be equal to the two equilibrium expressions times each other. So K reaction is going to be Ka2 times 1 over Ka. And that will be the mathematical expression. So what do I have? I have something times 10 to the minus 5th, and I have something times 10 to the 10th. Where does equilibrium lie? Equilibrium will lie this way, 10 to the 5th. 1.8 times 10 to the minus 5 times 10 to the 10th, we'll get about 10 to the 5th. So again, what we care about for organic purposes is figuring out which way equilibrium lies. Is this largely over here, or is this largely to the left? Is it mostly to the products, or is it mostly to the reactants? And so what you end up doing to make this easiest is you find the conjugate acid of your base. So whatever your base is, you find the conjugate acid, and you figure out what the pKa is for that. You find your weak acid here, and you know what the pKa is for that. So I have a pKa that's 10 and a pKa that's 5. And if I want to know where equilibrium lies, what the K for the reaction is, then I basically say, okay, the negative log of the K of the reaction is just going to be pKa2 minus pKa of the product. The difference is 5 minus 10, so the pK of the reaction is minus 5, so K of the reaction is 10 to the 5th. Said another way, there's 100,000 to 1. Reaction lies far to the right in this case. Do I want you to be able to do the math? No, I don't want you to be able to figure out what the actual K reaction for anything is. But you should be able to say, okay, yes, this will happen, or no, it won't happen. And it's useful to have a ballpark number. 10 to the 5th, it sounds like a really big number, and it is. But in the context where you have 10 to the 23rd molecules in a flask, or possibly 10 to the 21st molecules in a flask, if you're working on millimole scale, then 10 to the 5th is actually a relatively small number in that context. Even if you have 100,000 of these products for every one of these reactants, you have a fair number of reactants present, just because of the sheer volume of molecules inside your flask. So, what do you need to be able to do for organic reactions? First, I need you to be able to draw out the actual acid-base reactions. We will be doing mechanistic work shortly, so learn how to do that. But then, I would like you to be able to decide if a reaction is going to proceed to the right, will it go to products, or it will say largely unreacted on the left-hand side. That's really the skill you need to develop. And the reason why, and the way you're able to develop that skill is by looking at the pKa shortlist, which we'll talk more about soon.